The next presentation is leveraging the RISC-V Efficient Trace E-Trace standard. Speaker is Mr. Geir Eide, Tessent Embedded Analysis Product Manager, Siemens EDA. 次のご講演は、RISC-V Efficient Trace E-Trace という規格の活用です。講演者はシーメンス EDA、Tessent Embedded Analysis Product Manager のガイア・イーディ様です。Would you start?
Okay. Ready? Okay. Okay. You can hear me okay back there? Thank you. So again, my name is Geir Eide. I am part of the Tessent Embedded Analytics team at Siemens EDA. And that is a team that stems from an acquisition Siemens did a couple of years ago by a company called Ultrasoc. So I'm going to talk about trace, RISC-V trace. So this is a topic that should be of interest to those of you who either design SoCs using RISC-V cores, or if you develop software using that type of SoCs that have RISC-V cores. And the reason why I'm talking about this topic is that the team that I'm part of was one of the contributors, or a key contributor to the development of this this trace standard, what we call efficient trace, or E-Trace for short. And especially I want to acknowledge Ian Robertson, who helped develop a lot of this material and who also was essential in the development of that standard as well. So I'm going to talk a little bit about what trace is and why it's useful. I'm going to talk more about the actual E-Trace standard, and especially some of the capabilities or some of the things that are defined in the standard to make it efficient, and explain why that is important. So, as I said, this is a topic that's of interest to engineers who develop software on using embedded designs or for embedded designs. And understanding how that software behaves is always complicated, and it's always, always been complicated. The traditional approach to be able to debug software is to insert breakpoints and use a debugger. But there are many cases where that's not practical, especially if you're dealing with real-time systems, or if you have any type of time-based interactions between different components of a system. It's not practical to stop the processor to be able to debug it, because then you might not be able to resolve the actual problem you're chasing. So what you need in those cases is a way to observe, have observation like at speed, right? So you somehow record enough information of what's actually happened, so you can debug also speed related or at speed type problems. And to be able to do that, it's typically two conflicting requirements, right? First of all, you need to capture a lot of information so you really understand what happened, so you can debug the problem. But on the other hand, when we're dealing with embedded systems, we have very limited bandwidth. There's only so much information we can practically get out of the design. So processor trace is a way to deal with this. It gives you that visibility. It also has a lot of other uses for code profiling, for code coverage. But the key here is, and that we're going to focus on here, is the ability to have non-intrusive at speed visibility with a lot of what we call encoding capacity. That means a lot of compression, so we can effectively capture the information we need. And just to give you an example of the type of designs or type of scenarios where this is required, this is from a presentation that Richard Vaughan of Seagate did at the Siemens User-to-User conference in California a few months back. This is a presentation that's also available on the Siemens EDA website if you're interested in it. And the background here is that the majority of data in data centers today is stored on spinning disks on hard drives. And the requirements for performance and capacity continues to increase. So, mechanically, what's happening inside a disk is really impressive. Like the heads or the arms inside the drive have to move and be able to move it with nanometer precision, right? This is a mechanical arm, and you have to move it with nanometer precision. So this is handled by the controller in the drive, and so this controller needlessly has to perform a lot of very sophisticated real-time processing. And of course, at the same time, there are requirements for cost, for power and temperature and all of these things. So for the most recent generation of controllers, Seagate realized that they could no longer use the processor they had used for the previous designs. They needed something with more performance. And they chose to transition to RISC-V to get that boost in their controllers. And to be able to tackle this transition to RISC-V, they wanted to ensure that they also had the ability to debug and analyze software. Again, now when it transition to a new platform, you will have to either redo or rewrite your software or develop new software. And to make sure that they could do that effectively and also debug the types of problems related to real-time processing. Along with the transition to RISC-V, they also made sure that they implemented this in a way that where they also had the capabilities defined in this E-Trace standard. So how is trace typically implemented, right? So there's so the idea here again is that you capture certain information about how your program is executed on chip. So there's typically three components involved. The first bit is what happens on chip itself, which is that you capture and what we typically refer to as encode or compress data about the execution of the program. And that's done on chip, in hardware on chip, in what's usually referred to as in an encoder. And then that information needs to be transmitted out of the chip, usually to a host, and then you are decoding or really reconstructing what happened in the code. So using that log from trace along with original source code, you can put together, or software will put together exactly what happened to your program. And so again, the key components here being on-chip hardware as well as some external software. Now, there are many different ways that trace can be implemented. A very common method, and this is general, it's not specific to RISC-V, but a general method is what's called branch trace. So the idea rather than recording every single instruction that was executed in your program, you record what happens whenever there's a branch. Like, was that branch taken or was it not taken? And using that information, and the source code, you can then reconstruct exactly what happened. And I'll show an example in a minute. And one of the reasons why this is a common, or the most common way, is that it's very compressible. We'll show you some data about that as well. Now, so this RISC-V E-Trace standard, it defines like this particular compression algorithm, it defines the interface, but it also covers some additional capabilities that helps us compress the amount of data we need to transmit beyond branch trace alone. And it also supports data trace. So data trace means that in addition to tracing the instructions that are executed, you also, in cases of load and store operations, you record the location and the data that was stored. Now that's a lot more information. That's something that is less compressible and also therefore not used as much. So to give an idea of how this works with a little example, like when you create a trace log, when you execute the program, you will start off with recording the start address. And then again, we only record when branches are reported, like jumps or calls or returns and so forth. So everything else that happens sequentially is not recorded. And again, for branches, you only record whether a branch is taken or not. So there's only one bit of information per branch, except when you're dealing with indirect jumps. So branches or jumps that are taken to locations you can't directly deduct from the source code itself. And we'll talk a little bit more about that. But if you look at a very small example like this, some instructions here, you start out with first noting the start address. Then we start, as the program is executed, we'll go through multiple instructions that we will not put in the log, right? Because these happen sequentially. So we know from when we reconstruct the trace log, we know that given a source code, we know that these were instructed or were happened. And then we got a branch. In this case, because of the values in the registers, this branch is not taken. So we take a note of that in the log. We continue with some instructions we don't have to log, and then there's another branch that in this case is taken. It goes back up to line 14. And again, we go through this code again. We don't record that. Again, we get to the same branch, but this time it's not taken, so that goes in the log, right? So this gives an example of, again, it's a trace encoder on chip that will then record what's here in that trace log. Now, as I talked about, there are some, in cases of indirect jumps, that's where we have to record not just that the jump happened, but also the location, and that's a whole lot more data. So we'll talk about how can we do something about that as well. But this was kind of an introduction to how trace is implemented in general. Let's talk a little bit about the standard. And of course, what's unique about RISC-V is, again, it's an open architecture, an open standard. There are many, if you design a chip with RISC-V, you can choose to implement it itself, or you can use in one of the many vendors. You have many options in terms of optional instructions and so forth. And that also poses some additional or some interesting opportunities for everything around the whole ecosystem, right? Then in addition to the instruction set architecture, what's important about RISC-V is the ecosystem around it. So to be able to have a successful debug and trace solution, it's important that this also happens in a collaborative environment like the instruction set architecture itself. So the efficient trace standard, again, is a result of that type of collaboration. I'll go through the timeline here in a little bit, but it defines the actual algorithm of the trace. So what's being implemented in the trace decoder, again, in addition to defining the interface also between the CPU core and the trace encoder. And that's what makes it possible to, for instance, for two completely different organizations to design the actual core and the trace encoder. So the origin of this standard came from Siemens or Ultrasoc before Siemens acquired it, and was then donated to the RISC-V community, and has then been kind of tweaked and enhanced by the community itself. And the work here started about 8 years ago, and then first, what was an Ultrasoc introduced the first trace encoder for RISC-V. The standardization group was then formed later the same year it was introduced. And then since then, there have been like development and what happened in our team, and lots of new capabilities were added to our solution, but also to the standard itself. And the most recent, this has kind of been going on. The most recent version of the standard was released in 2022. And right now there's an extension work going on to that, defining how the actual encapsulation of the packets, of the trace packets, how that is done as well. So the standard are additions that go into the standard and also into the actual solutions. Now, so a key component in trace here is how effective it is. How little information do you actually need to send out of the chip? And what you're looking at here, if you look at the rightmost bar, the darkest blue bar, what that tells you is, or what this chart shows you, is how many bits per executed instruction in a program is being transmitted in a trace log. So what that means is about a quarter bit per instruction, or 1 bit per every 4 instructions with the most recent version of the standard, which is an improvement to about half a bit per instruction in that first RISC-V trace encoder. And then there's some comparison here to some older or some other types of solutions as well. So again, this is because you're only like recording when the branches are happening, like you're not recording something for every single instruction. And again, the whole reason why this is important is that the more compact this information is, and while still maintaining enough data to be useful, the longer you can trace, so the longer part of execution can you keep track of, and then less bandwidth do you have to use. So if we look at what's actually in the standard, there are some mandatory capabilities, and there's a bunch of optional capabilities. And again, the idea here is that given the standard, like it defines what the trace encoder needs to do. It's enough information in the standard to be able to implement a trace encoder and to be able to implement the decoder software. So the basic idea here is that in the mandatory features it covers instruction trace. It covers the actual interface between a CPU and a trace encoder. And it also implements defines the actual algorithm and what we call a packet format, so the format of the actual trace data. Then there's a series of optional features that in the trace standard. And typically you would, to the extent you need those, depends a little bit on what type of SoC or design you are developing and what your requirements are. And the reason these are optional is, of course, that these will impact the complexity of the trace encoder and the amount of area overhead as well. The first feature here, multiple instruction retirement, again, that's that relates to superscalar designs, where you can execute more than one instruction per cycle. Data trace, again, this is the ability to also trace or to capture the location and the content of data, and for read and write locations. Again, this is not as compressible. It provides useful data. We see that maybe 10 to 15% of our users use data trace. And then there's a set of additional capabilities that relate to the compression or to what we call encoding capacity. So again, these optional capabilities allow you to record less and less data, and we'll talk about a few examples. Something that is not in the standard, but that we have implemented in our solution, is something called cycle accurate trace. This means that in addition to capturing what happens, when it happened. This is useful, especially in debugging kind of dealing with time critical problems. So for instance, if there's a stall, you know, for what instruction the stall happened, for how long was the stall. So for performance, high performance applications, this kind of helps you tweak and get the most out of your software. So let's talk a bit more about efficiency, right? Because we said for all-way trace here is jumps and when these are taken and not taken, but when there's ambiguity of where that jump is to, right, you need to also capture the address. So no, most pieces of software consists of a lot of functions, and when these functions are called, you have to make note of where is the next instruction, right? And then you jump over to where the function starts, and at the end you return. Then you have to go back to where that next instruction is, and that's usually an implicit return, and therefore it means that the location of the return address has to be captured in the trace code. And again, this adds to the amount of data that has to be captured. So a way to address that is to maintain a stack, again, in hardware, in the trace encoder, of where the return addresses are. So you don't have to actually report that in the log. You will only report it if the return is not where you expected it to be. And this typically, has a good impact on the amount of data you have to capture, and I'll show in some examples. The other thing that can also help is something called branch prediction. So the idea here is that, normally a branch, you only capture one bit of trace, which just very little, sounds very efficient, right? But if you have a very tight loop where you repeat on this loop a lot, that can still result in a lot of, because then there's a lot of branches, and you again need to keep track of did it happen, didn't happen, and you end up with 1,000 bits right before you know it. And the idea here is that with a predictor, where you basically predict these branches, you can now, instead of recording each branch, just record when the prediction fails. And this, again, you need a very simple predictor to do this. Is very different than what you usually see and implemented in CPUs. But for certain programs, this also has a lot of benefit. And also something kind of somewhat similar to kind of the opposite of implicit return is having a cache of the jump targets. Again, this, imagine if there is a function that you jump to from many different locations in your program, right? So there are many locations in your code, you jump to the same place, and you can keep a cache of that, and then in the log, capture just the index of the cache rather than the address. So again, these sound like very insignificant little improvements, right? Where you just reduce the number of bits you need to capture, but they actually have impact. And we did some experiments using, this is just a kind of a standard benchmarking suite. I'm not going to go through every single the numbers. We can look at them graphically. The idea here is that, again, we're sorting at, or we're looking at the number of bits per executed instruction. So again, the smaller is better. The dark green bar here is just using the required features in the Efficient Trace standard. And you will see it varies a lot from 0.01 and all the way to 0.5. Again, it depends on, again, this is just the branch trace, right? So really imagine if there are no branches, then there's not a lot of information to capture. The shorter bar here is with the extensions, right? So those things I just talked about, right? So you see there's a good impact here in some cases. And in particular, now we're just looking at the additional improvement in efficiency for some of those enhancements, like you're breaking it down into the specific optional capabilities in the spec, where the left graph for each of them is the average impact, and the big graph is the like the test case, so the specific benchmark where we had the greatest impact. And you'll notice, for instance, implicit return has a good improvement across the board, quite a bit in some extreme cases. Branch prediction and the others not as much. But the other factor to take into consideration here is that if you use these extensions, you add a little bit more extra area overhead on your design. And implicit return is typically the biggest one, branch the smallest. So in summary, understanding software behavior and in complex system is extremely challenging, and especially for real-time systems, you need a non-intrusive, full-speed observation of behavior. And again, being able to do this with as little, be able to have to collect as little data as possible is a benefit. This is just part of the problem, right? Again, this is focused on just processor behavior. There are other challenges you're dealing with in SoC and system debug and optimization. And just to have a little advertisement for our product line here, that's also part of what we do. We just don't deal with RISC-V, we deal with the entire SoC. So with that, I thank you very much for your attention. And if there's time for a question, I'll try to answer it.
So thank you very much. So our session is now open for the questions. So please raise your hand when you ask questions. So.
And if you want to ask questions in here, we have a booth outside, so we'll be happy to talk to you one-on-one as well.
So may I ask one question? So
absolutely.
Okay. So I have only very little knowledge about this kind of technology, but basically what you are proposing is kind of based on RISC-V trace spec,
right?
And improve more, trace bit efficiency by defining your company, right? So right. This is a value proposition of yours.
Yeah. So the value proposition is twofold. First, to use trace to make debug easier, and the second part is that by using these additions to what's in the spec, trace becomes better because you collect less information.
So your product does not harm any RISC-V standard things. So no, basically just upper compatible stuff, right?
Yes. So our products are based on the standard, so are fully compliant with the standard, and also has some additions beyond what's in the standard today, but that also might be in the standard in the future.
Okay. はい。他にご質問ございますか？では、Okay, so let's close the session. Thank you.
Thank you.
So let's take a 15-minute break. The session resumes at 3:10, 3時20分にまた始めますので、お疲れ様でした。